this last section is about dependent and independent events. The independent events are pretty easy. It means one event has no impact on the outcome of the other event. Independent events would be like flipping a coin and rolling a die. What's the probability of getting a heads when you flip a coin? 1 and 2, 1/2. What's the probability of rolling a 2 on one die? So what's the probability of going heads in a 2? Would be 1/2 times 1/6. You have a 1 in 12 chance of that happening. So independent events. When I flip the coin, that has no bearing on what happens when I roll the die. The coin, the outcome of the coin has no impact on the outcome of the die. That's why we call them independent events. One outcome has no effect on the others. So if you're looking at independent events and you want to find out the probability of A and B occurring, the probability of A and B occurring, you multiply the probability of A times the probability of B. They are treated independently as well. So here's the probability of A, here's the probability of B. They have nothing to do with each other, and you multiply them together. So if you look at a situation with 2 die, and we've done this already, we roll a blue die, we roll the red die. What's the probability of the blue die landing on a 3 and the red die landing on a 4? Okay? Do these outcomes depend upon each other? Do the outcomes depend on each other? No, they're totally independent. What's the probability of getting a 3 on the blue die? 1 in 6. Times the probability of getting a 4 on the red die. 1 in 6. So that's going to give you a probability of 1 in 36. This is the probability of a 3 on the blue, probability of 4 on the red. When you multiply them together, the chance that you're going to get a 3 and a 4, 1 in 36. 3 on the blue, 4 on the red. Any questions on that? And the outcomes, are they dependent upon each other? Not a chance. So we're going to do a fundraiser and sell raffle tickets. You can buy raffle tickets for a gift certificate at the mall, or you can buy raffle tickets for a pack of movie passes. You buy 5 of each raffle ticket. What's the probability you win both of the prizes? So we want to find the probability of win-win. Okay? So you have 5 raffle tickets for the gift certificate. What's the probability that you're going to win? 5. Anyone not seeing that? What's the probability that you're going to win the movie passes? 5 out of 200. You're going to multiply those independent probabilities together. You can reduce first if you want. You can multiply, then reduce. Doesn't really matter to me. 5 out of 150 is 1 in 30. 5 out of 200 is 1 in 40. And you end up with 1 in 1,200. So many times you feel like, oh, I got to go right to my calculator, and it's not faster to do that. So the probability you win both prizes, you get a 1 in 1,200 chance. If you want to increase your chances, what should you do? Buy more tickets. Questions on this? Independent events, pretty easy. It's when they become dependent that we get confusing or more confusing. So you have 50 out of 75 guys said they want to, or that they like the school mascot, and 40 out of 50 women said they like the school mascot. if you choose a male and a female at random, what's the probability they both like the grizzly? Probability a male who likes and a female who likes. What's the probability you get a male that likes the grizzly mascot? 50 out of 70. So 2 of you will understand this. The rest of you, not so sure. What's the probability that the female you choose likes the mascot? 40 out of 50. So again, independent, what happened with the guy doesn't have any impact on the girl. We can multiply, we can cross cancel first. The 50 certainly can go. 40 over 75 are both divisible by 5. So you get 8 and 15. So the probability you're going to choose a guy and a girl who both like the mascot is 8 out of 50. Everybody good with that? These are independent. So what happens with one has no impact on what happens with the other. This one gets a little bit more complicated, but again, there are 3 totally independent events. And you know, there are people out here, even though the events are independent, people feel like your probability increases when something doesn't happen. You flip a coin, you get heads, you get heads, you get heads, you get heads. You ask some people, what's the probability the next one's going to be a tails? Is it more than 50%? Oh yeah. You better believe it's more than 50%. We haven't had a tails in a long time. You had 5 heads in a row. Are you kidding me? You've got to get a tails. It's got to be more than 50%. It's not. Independent events. So you have a group of track members, and this one particular racer is going to do 3 separate heats. And the assigning of lanes is done randomly. And there are 8 lanes. What's the probability that for all 3 races, this poor soul got into lane 8? What's the probability he gets in lane 8 in the first event? 1 out of 8. So if you look at this racer, we want to know what's the probability that he goes lane 8, lane 8, and lane 8. The probability in the first race that he goes lane 8 is 1 in 8. The probability he goes lane 8 in the second race, 1 out of 8. And in the third race, 1 out of 8. So if you multiply those out, top's easy, bottom 1 in 5, 12. Not a very likely occurrence.
Where did you get the lane?
There's 8 lanes. You're going to get one of the lanes, right? What's the probability that you get lane 8? You get 1 chance out of 8 possible.
Oh.
So you get a 1 in 8 shot of being assigned lane 8. But you get a 1 in 512 chance of being assigned lane 8 3 times in a row. What do you think? Were you thinking it might be dependent? That's where the issues arise. Did you have some feeling that maybe it wasn't independent? Oh yeah, we haven't done the dependent. These are all independent. These outcomes are all independent. Okay, whatever happens in the first event has no impact on the second or the third in this case. Okay, so 46% of parents say that they read to their children at least once a week. Once a week? Holy smokes. If 3 parents are selected at random, what's the probability that all 3 will say they read to their children at least once a week? We're doing the probability read, read, read. What's the probability the first parent reads to their kids? 46% or 46 out of 100, whichever way you want to do it. You can either write it as decimal or as a fraction. Doesn't matter. Second parent is also 46%, and so is the third. once a week. Parents are supposed to read to their kids 1,000 hours before they enter school. You're supposed to read to your kids 1,000 hours before a kid goes to kindergarten. So once a week ain't going to do it. And when you start to do the math on that, you better be reading an hour a day practically in order to get your kid ready to go to school.
Or we want the answer.
If you want to tell me the answer.
All right.
Seem to.
It's 0.097.
Oh,
Yeah, 0.0973.
or what?
36.
36 what?
No, 336. So like 0.09736, and that's it.
So that would be a 97.336% chance.
No, 9.
Oh, 9.7. Got it. Seven, 3, 12, 4%. Any questions on that?
I have questions around these kind of questions.
Well, there's no way to not, is there? If you're using the decimals, right? No way to not round. So if you want to change them to fractions, if you were doing fractions, you could leave it as an unreduced fraction. That would be fine. But I'm fine with you going with the decimal as long as I have 3 places. Okay, so now somebody asked about the complement earlier. This is a complement situation that we're looking at here. It's kind of confusing, and it's really confusing to do it without the complement. So you have your iPhone, you're riding the bus to school each day, and you have time to listen to 4 songs from this playlist with 16 songs in it. What's the probability you're going to hear your favorite song at least once during the 5-day school week? So assuming that in the 4 songs that you hear, there's no repeating, and assuming that each day is a new day, and what happened on the first day doesn't impact on the second day, what's the probability you're going to hear your favorite song at least once? Well, in order to do that, you would have to find the probability of hearing your song how many times?
Oh,
Once, twice, 3 times, 4 times, and all 5 days that you heard your song. Okay? It's going to be quite the challenge. It's much easier if you're doing the probability of hearing your favorite song at least once. It's going to be way easier to do 1 minus probability of not hearing favorite song at all. Rather than figuring out what it would take to hear your favorite song once, or twice, or 3 times, or 4 times, or 5 times, let's do probability that we're not going to hear it. And we subtract that from 100% or 1, and that'll be much easier. Now, in the playlist, there's 16 songs. How many ways can we have a group of 4 songs play? How many ways can we have a group of 4 songs play on any given day and not have your favorite song be in that group? And it should be a pretty significant number. It should be pretty big.
Well, when you do the combination of 16, like we're getting 4 out of that, or 16 combination 4. How do you say that, by the way?
16 combination 4, I would say combinations of 16 items taken 4 at a time.
Okay.
Or you can say what you say. But that would not give you the number of ways that you would hear 4 songs without hearing your song.
Yeah, I guess.
That would be 15 taken 4 at a time.
Would it be permutation or combination?
No, because it's a combination, because the order in which you hear the 4 songs is irrelevant. It's just to hear your favorite song, or in this case, when you choose your 4 songs, which way did you hear them? So it's a combination. Now, how many ways are there to listen to the 4 songs in general? That's what? How many ways on your iPhone can you listen to 4 songs from this playlist?
Combinations of 16 and 4.
That's the 16 taken 4 at a time. That's the total number of ways you can hear 4 songs on any given day.
How would you write it like that?
How or what? How do you want to write it?
Well, I'm just asking.
Okay, well, I'm just asking what are my other choices?
Why would you want to write it as a fraction like that?
Because that's what probability is, favorable outcomes over total outcomes. This is the number of ways that we can listen to 4 songs without hearing my favorite song.
Okay.
And this is the number of ways I can listen to 4 songs, maybe my favorite song is included. Okay? How many days are we going to do this? 5. So you need to raise this to the 5th power. So the probability for Monday times Tuesday times Wednesday times Thursday times Friday subtracted from 100% is what we're looking for. So work-wise, I'm okay with you going now and saying this is going to be 1 minus, what's the number for combinations of 15 taken 4 at a time? How many? It's going to be like, really?
Yeah.
1,365 over 16 taken 4 at a time? 1,000? Now, at this point, you should make that fraction, 1365 over 1820, to a decimal. And raise the decimal to the power of 5. So 1 minus 0.7.
Or that's just the decimal. 0.75.
I want to know what you get when you raise it to the 5th power.
0.2373.
0.2373, keep going.
0.4688.
Okay? So that decimal keeps going. This whole decimal is what you want to subtract from 1.
0.7666 times 3.
That's good. And if you wanted it as a percent, it'd be 76.270%. That would be the probability that you're going to hear your favorite song at least once in the 5 days. More than 3 in 4 chance. Better than 3 in 4 chance. So maybe if you did this every day for 4 weeks, one of the weeks you wouldn't hear your favorite song. Any questions on that? Okay, so now we'll go to dependent events. So dependent events. Some of you, if you open up your drawers in your dresser, you have a socks drawer in there somewhere, or maybe half a drawer filled with socks. If you're like me, you reach in and you pull out a pair of socks. Because my socks are together. Some of you have the drawer where you take the socks and dump them in without ever matching them up, and you pull out a sock and then you go rifling through to find the other, although I was informed by one kid, I only have one kind of sock, and they're all the same color, so it doesn't matter. When I pull out 2 socks, I automatically have a match. Okay? But I know some of you have sock drawers with multiple kinds of socks. So now here's the deal. If you pull out a sock, and you're holding it in your hand, and then you pull out another sock, the probability that those 2 socks match are dependent. Because you reached into the pile, pulled a sock, and then you reached into the pile that has 1 less sock in it and pulled out a sock. So the probability of your second sock is dependent upon what happened on the first sock. Does that make sense to everybody? If we have a deck of cards, what's the probability in my deck of cards that I reach in and I pull out a spade? 1 out of 4. Could you reach in and pull a spade out for us, please? Okay, so Samana's not very good at this. Be patient with her. A spade, please. Look, let me show you. That's what spades look like. I need you to get me a spade right now. You only have 2 more chances. Atta girl. So we got a spade. Now, if we take her 9 of spades and we put it back in the deck and we shuffle, what's the probability she pulls a spade on this card? 1 in 4. You're not very good at this, Samana. Try again. This isn't that hard. There's 13 of them in here. I just want 1 of them. There's a 1 in 4 chance both times. What's the probability she goes spade, spade if we do pull a card, put it back in, pull a card? 1 in 16. Get a spade. Samana, you're killing me. Okay, spade. It's random, Samana. Now the pressure's on. I can't get a spade. You're good at the clubs. We should have gone clubs. Okay, I'm going to second. Give me a spade, please. Samana's fired from pulling spades out of here. Ace of spades, okay? So now give me another spade. 10 of hearts. Not very good. But if we wanted to go spade, spade, and she keeps that ace of spades, what's the probability that her first card was a spade?
1 in 4.
That's 1 in 4. What's the probability the second card is a spade?
6
12 out of 51. There's only 12 spades left in the deck. She has the ace. And there's only 51 cards left in the deck because she has the ace. Okay? No, she only has 1 of the cards. She pulled the ace, she had it. When she pulls the second card, there's 51 cards.
Oh, okay.
She didn't keep that heart and then pull another one. Okay? So when we do probability of dependent events is where the second event's outcome depends upon the first event's outcome. That's called conditional probability or dependent probability. It's typically written like this with the vertical slash between the B and the A. And it usually means the probability of B given that A has occurred. The probability of B given that A has occurred. So when you want to find the probability of A and B occurring, A being first, you find the probability of A occurring, then you find the probability of B occurring given that A has already happened. And that gets kind of confusing. So don't feel bad about making me re-explain problems. And if you don't get a good explanation, maybe you need to come and talk to me and I need to try some different things with you. So, dependent events. You have a table here talking about registered college students. What's the probability that a randomly selected student is? First, we're going to do female. What's the probability that you're going to choose a female? Look again. Not 80 out of 140. Oh, wait. 120 out of 200. You have 120 women, 80 part-time and 40 full-time, out of the total student population of this survey is 200. So 120 out of 200, or what is that, 3 and 5? Okay, so you have a 3 and 5 chance of getting a female. Now, what's the probability that you're going to get a full-time student if you are choosing from the females? What's the probability that the female is a full-time student? Given that it's a female, what's the probability you're going to get a full-time? No. No.
1 and 2.
Let's not use 1 or 3s or numbers that small because none of those numbers are on the board.
40 out of 120.
40 out of 120. So we want 40, that's the full times out of just the women now, 120, which reduces to 1 and 3. Everyone follow that logic? You can only choose from the females in the B question. Now, there's not really 2 events going on, so this kind of a question not really as logical as what we want here.
Yeah, can you just like use the table and just put 40 out of 200?
Yeah.
One more time?
Yeah, where it says, oh wait, oh, if, you know, what I thought it said like, what's the probability of the female and full-time student? Couldn't you just use the table that asks that?
I still couldn't hear your full question.
Oh, like, I thought you said, like, what's the probability of one being female and a full-time student?
No, if it's a
Yeah,
female.
okay.
Right, and that's, all it takes is misreading one
Yeah.
word, and it blows up your whole problem. Of course. So now we're back to 2 cards. Now notice the way the question's worded again. There's 2 things going on when we look at these. We're going to draw 2 cards. It says, what's the probability the first card is not, that should be a heart, and the second card is a heart if. The key is if you do replace, and then over here it says you do not replace. So you need to pay very close attention to whether or not you have replacement, excuse me, or you don't have replacement. In this first one, we're putting it back. That's what we were doing with Samana, the first go around. The second time, we didn't put it back. That's what Christy did. So when we look at this, if we want to say, we want to go standard deck of 52 cards, and we want to go, first card is not a heart, and the second card is a heart. So we want to do probability of not heart, comma, second card is a heart. What's the probability the first one's not going to be a heart?
39.
Again, we got 2 people who are playing the game and a lot of people riding the bench. Not going to be very functional for you. For not a heart, there's 39 cards that are not hearts. There are 52 cards that are. The chart is shown, or the little graphic off to the right here. You got to know your deck of cards. On the second card that you pick, what is the number of, or the probability your second card is a heart?
13 out of 52.
13 out of 52. Again, you can reduce these to 3 and 4, and 1 and 4, and you're going to get a 3 out of 16 probability if you go no heart, not a heart, and heart. So you have a 3 in 16 chance of that happening. Now we're going to do the same thing, probability of not a heart, and then a heart, but this time we're going to do it without replacement. You do not replace the card. The not a heart probability is what? Doesn't change. But the heart probability changes. What will the heart probability be?
12 over 52?
Close.
13.
13. The 13 is the heart, because we did not pick a heart in the first one. But we did pick a card which dropped us to the 51 in the denominator. Now you can reduce as much as you want. Again, sometimes going to the calculator is not really the way you want to go. We can cross cancel the 3 and the 51. And you're going to end up with 13 over 68. So 13 and 68 is your chance. Which is better probability? Not hard with replacement or without replacement. If you're asked to compare them, I don't know about you, but if I'm comparing 3 and 16 and 13 and 68, I'm not very good at comparing those. What should you do? Switch them to decimals and see who has the better probability. Any questions on this example? Find the probability of going spade, then club with replacement, and then spade, then club without replacement. So we're going to go probability spade, club, doing it with replacement. Stephen, would you go for probability of spade? 13 out of 52 times probability club. Also 13 out of 52. That'd be 1 in 4, 1 in 4. A 1 in 16 chance with replacement. Natalie, how about without replacement? What was your, if we're going to go spade, club.
13 out of 52 and 13 out of 51.
13 out of 51, and how did that reduce for you?
13 over 4 times 1 over 4, which is 13 over 204.
13 over 204. 13 and 204 would be the probability that you could go spade club. No, it's not an assumption, it's a fact.
Oh.
Because we're doing probability, not maybe.
Oh.
So if we're saying spade club, this is the probability we did get a spade. It's in my hand now.
Okay.
So then there's still 13 clubs left in the deck, but there's only 51 cards, and one of the cards that's not there. Now, I'm not arguing with you that it could, no, I don't mean it, like, I'm just saying, if you're absolutely right, how are we sure that it's a spade in our hand? When we're doing probability, you're sure. It has to go this way. But I have the same apprehension. So you and two friends go to the same store at different times to buy prom dresses. Find that hard to believe. There are 15 different dresses at the store, and the store has at least 3 duplicates of each dress. So that means everybody could get the same dress. What's the probability that you each choose different dresses? And what's the probability that you each choose different dresses? Okay? So there's 15 different dresses at the store. The store has at least 3 duplicates of each dress. What's the probability that you each choose different dresses? So we're going to go probability of 3 different dresses. Okay? So you got to figure out how many different ways the 3 of you can choose different dresses. How are we going to do that? How many ways? You could do the fundamental counting principle, or you could do permutations, 15, taken 3 at a time. That would be how many ways you could have 3 different, or the dresses assigned to 3 different people in different, so no duplicates.
Aren't there 45 dresses?
There could be a million dresses here. We're just talking about if there's enough so that everyone could get the same. Okay? How many ways are there for the three of you to choose dresses? You're misunderstanding my question. Are you telling me that that's what that is?
Oh, gotcha.
My question is, how many ways could the three of you come back with dresses? How many ways?
Permutations.
Nope. Nope, I just want to know how many ways you could get dresses. The different dresses is on the top. How many ways could the three of you come back with dresses? No. 45. You need to, if you think there's 45 dresses in this store, you're misunderstanding what we're trying to tell you. How many ways can the three of you come back with dresses? Not 3. That's how many ways you could pick the dress, Stephen. How many ways could I pick my dress? How many ways could Spencer get his dress? How many ways could the three of us come back with dresses for the prom? How'd you get it? 15 cubed. Okay. Another option would be, like Paige suggested, go counting principle. How many choices does Stephen have when he goes to get his dress? 15. How many choices did I have when I went to get my dress if we're doing on the top different dresses? 14. We don't want to go and arrive with the same dress. And when Spencer goes, how many choices did he have? 13. On the bottom is how many ways can you get the dresses with no restrictions? That would be 15 times 15 times 15, or 15 cubed. Either way, whether you use the permutation or whether you use the counting principle, doesn't matter to me. On the top, how many choices will we have? And on the bottom, 75?
Yeah.
Okay, and I'm sure that can be reduced. Okay, 182 over 225. Pretty good chance that we could get 3 different dresses. Right?
So the whole like duplicate tables there just throw you off.
Well, you're talking about this 15?
I'm talking about like 3, like it says
Of
on
the
store.
duplicates?
Yeah. That's,
What we're trying to tell you there is that there are not just 15 dresses
Oh, yeah.
hanging on hangers. You have an infinite supply. It really needs, you need to understand there's 15 styles. Obviously, Stephen and Spencer are not wearing the same size, right?
yeah.
So we're just telling you that everyone can get the same dress, and it doesn't, we have an, it's unlimited supply of each dress. If there were 15 dresses, this word, these don't mean, and that has nothing to do with this problem. It's just so you can know that every single person can get the same dress. When Steve, no, it's really not. It's meant to be more of a clarifier. I want you to know that when you walk in the store, there are not, literally, count the dresses, there's only 15. And if there were 16 customers, somebody doesn't get a dress. That's what I want you to understand. Sometimes we overthink it when we try to write the problem. Okay, so this is the assignment that goes here. Test is Wednesday.